Hello, hello, and welcome back to the Legal Grind. Today we have 648 replace words. It says here that in English we have a concept called root, which we which can be followed by some other word to form another longer word. Let's call this word derivative. For example, when the root help is followed by the word full, we can form a derivative helpful. Given a dictionary consisting of many roots and a sentence consisting of words separated by spaces, replace all the derivatives, so the longer versions in the sentence, with the root forming it. If a derivative can be replaced by more than one root, replace it with the root that has the shortest length. So we're optimizing for the shorter length. And then return the sentence after the replacement. The key is that the sentence is a list of words or words separated by single spaces. Okay, and then we have some examples here. We have a dictionary with cat, bat, and rat. We have a sentence here where the matching words, the words that don't have a root that begins with any word in the dictionary, those are used in full. Those that do have a corresponding version in the dictionary, we take the root and replace the original longer word with the shorter root. And if there happens to be multiple, then we just take the shorter of the options. Like let's say instead of cat, there was also cat in, for some reason, CATT. Then let's say like this happened to be mm, that. Then cattle would match cat with two T's and with the one T, but we would optimize for the shorter length. Okay, now that that's out of the way, there's a simple way to do this, and there is the preferred way, I guess, which is using the try. The try is actually not that complicated, it's just longer, but let's hone in the concept by going over the brute force way first, which is okay. So we're given a sentence, which is just a string of words. All right. So why don't we break that down? Let's grab the parts from it. The sentence dot split, and this works because they are separated by single spaces. Great. And now let's get the words in the dictionary as a set so that we can do a quick lookup. Okay, so we have those. And then let's have some helper method that basically takes in some parts and goes from starting with just the first character, then two characters, and three, all the way until you reach the full character. And the first part, uh, the part of the first part that matches any word in the dictionary, let's return that. And then ultimately return the sentence joined back with single spaces. So this is the helper. So let's say shortest, um, find, shortest matching. Shortest matching, let's say, and we'll take in some parts, some original word. And we'll say for I in range of 1 to the length of the entire full, so one character to the entire full, we'll say if full up until that character position is in words in our set, our dictionary, then we just return it. And this way we can optimize for the shorter length. Oh, like that. Now, otherwise, we continue searching, and if we don't find anything, ultimately, we return the full word. Okay, now for the actual return logic, what we're returning is single white space joined list of strings. Now, what is this list? This list basically takes, every part in parts where parts is the parts of the sentence, and then it applies this helper function on it. So shortest matching parts or parts and parts. So we get the shortest matching version, the roots for every part and parts, and then return it joined once again. Let's try that. And let's give it a go. Okay, so that does work. And now and now let's go over the try, which is a similar idea, but we're taking advantage of this structure. This itself is from Shrina, from this Medium article, very helpful. And basically, whatever words we have here, let's say cat, bat, and rat, we're going to start the try structure with some note, which will just have two characteristics, whether or not it itself represents the end of a valid full word and a pointer to its children, the children being A through Z. So here we have A to B, then we're assuming that C is none, D is none, like so. And then we can build out, like if this was cat, then we would have a C here, which points to an A, which points to a T, so that cat is one word, but if this were to go on with another T, LE, and form cattle, then we don't need to keep searching from the beginning. We can take advantage of this structure. Okay, so let's give that a go as well. Now for that, we do have to do some setup where uh, first we have a try node. A node, once again, let's initialize it. A node, once again, has two attributes, whether or not it represents a valid end. So CA, at this point, A would not be the valid end, but T would be. And then if cattle itself was a word, then E would be, but then the T and L, these would not be valid ends. So self.end, the default value is false. It is not a valid end, and itself has a pointer to its children, which are the 26 lowercase English letters. Lowercase English letters. Okay, now we have the try node. Now let's create the try structure. So this is the actual tree, which we initialize simply with the root. And we initialize the root as nothing but the try node. And that's it. And now we do need some helper functions to insert words. So we'll be inserting every word in the dictionary to this try node to form this kind of a data structure. So let's say, all right, we're going to start the curve pointer at self.root. And then for every character in this word that we're trying to add, we're going to say, first of all, does that next character exist? Here, this starts with, pointers to all the characters in the alphabet A through Z. Does this character exist in this guy's children? And if not, well, first we need to initialize an empty try node because essentially we want to start from the root and then keep jumping to the next guy. And at the end of the word, mark that as the end. That's our goal. So to do that, we first need to ensure, this is a safety check, that there is a node that is there in order for us to jump to. So if not, cur.node, and we're going to do ord of this, which will just give us the ASCII number. So ASCII number of, for instance, A is 97. So if we minus ord of A from, let's say A, that would give us 0. B, that would give us 1. and that just gives us the indices for here. So if that child does not exist, then we just add it. Current nodes, same thing, ord of that character, minus ord of A, just to get the index. We're going to initialize it to an empty try node. And now that we know that this try node exists, whether or not because we added it or it was pre-existing, we're going to say, great, now we're going to jump to it. So now our current pointer points to that next character. And this just once again gives us the index. And then once we've exhausted every word, character in that word, then we can finally mark the current node's end to true, which otherwise is false by default. So let's do that. And then finally, the last helper that we need is the one that basically we use to find the shortest route, where we'll take in some word. It's similar logic to here, but the only difference is whereas here, if the next character didn't exist, we added it in order to jump to it and ultimately mark the end as true. Here, instead, as soon as we find a character that is not there, we can basically say, hey, you know what, there's no word here that matches the beginning here, so we just return the full. Otherwise, we continue jumping, jumping, jumping until we find some word that is fully the end, where that node is the end, it's a valid full word, and then we can return that. This will make more sense. So we initialize it as the root. We point to the root to begin with. Then we want the indices. So for I, char, and enumerate the word. So we'll get the index and the character. We'll say, you know what? If not cur.nodes of or of this character minus or of A. So if that child at that index position does not exist, you know what? We can't find the match, just return the full word. Otherwise, we're going to jump to it. Cur.nouns or the character minus or of A to get the index position. And then here's the thing, we're iterating and we're saying, you know what, if curve wherever we are, we jump to a new node, right? We jump to the next character. If where we jumped happens to be an end, then we can return the word up until that point. But remember, we're at that word and this is exclusive. So +1 to return that character as well. Now let's say we went through the entire word and we couldn't find a match. That's okay. So we just return the word in full. So this means there were a part, like CA was there, but let's say we were targeting CAT, but this was CAP. Then we say, ultimately, we didn't find the full word, then just return the full word, or the original word. And now we have the try node that has the two attributes. We have a helper to add the words. We have a helper to find the shortest route, and the rest is easy. All right, same thing. Let's get the parts of the sentence. Sentence dot split. Then let's initialize our try. And then what do? We first add all the words. So for word in dictionary, we can try dot add our word, taking advantage of this helper function add. And then all we do, similar to the first way we did things, we're going to return something. What we're returning is a space separated list of words. And what is that list? That list is nothing more than some operation we've performed on every part in parts. And that operation is try the shortest route of that part for part and parts. And that's it. So we've added every word to the dictionary. So we have this guide that we can go through. Then we just apply the shortest root function, join it back together with single space. Let's see if we have any errors. Okay, looking good. And there you have it. This was 648, replace words. See if I can get this all in one screen. And there you have it. Thanks so much. Happy coding. See you next time.